Thank you very much for the invitation. It's a pleasure to be here. So, can you see this?
Yeah,
can you hear this?
They don't ask them because they don't have microphone.
Okay,
Yes.
it's okay. Okay, so they will tell. Okay, fine. Okay, so my title is Equivariant D cap modules on rigid analytic spaces. So I will try to explain at least what cap means. So it's not D modules, it's some variant of D modules. I'll start with some motivation. Bang. Sorry. So the motivation in this story comes from the desire to understand the representation theory of p-adic groups. So, well, some branch of. Let me be more precise. So L will be a finite extension of QP. K will be some complete and discretely valued field extension. For simplicity, haven't had time to work out all the details yet when K is more general. So L will be the field of definition of the group, and K will be the field of coefficients in which the representations are taken. G will be a connective, inductive algebraic group, and Roman G will be some open subgroup. For most of my life, in fact all of my life, I have worked with compact p-adic groups, but I am now understanding that the theory should extend quite naturally to the general case, but in my mind usually G will be compact. So the problem is to understand the following category of representations: admissible, locally analytic, locally L analytic K representations of G. I will not give the definition of this. I will only say that it's the opposite of the category of coadmissible modules over the so-called locally analytic distribution algebra of G. So let me write that down. Oops. Has been defined by Schneider and Teitelbaum about 13 years ago, so 14, 15 years ago. It is some kind of distribution algebra. It's the strong dual of the ring of k-valued locally analytic functions on the group G, and I think of it as some completion of the group ring of G. So I don't want to spend my time discussing the beginning of this theory. It's sufficient to just think of it as a completion of the grouping.
So this kind of distributions which are supposedly of compact support, or not? Can you give an idea geometrically about those distributions?
Yes, I think of compact support, yes. So
Okay.
you take the, you do define it for compact groups first, and then you take the direct limit over all possible open compact subgroups inside of the general G.
Okay, so for a compact group, it's like functionals and local analytic.
Functionals, for a compact group, it's functionals on the locally analytic functions on the group, yeah.
Yeah, which are continuous when you fix radiuses of convergence or things like
Yeah.
this.
Yeah.
Okay, I think I understand.
So, hopefully you will see the net flavor of it in what follows. Whatever it is, it's a Frechet space over the ground field K, and it contains the abstract group ring of the group G inside it.
Is it important to say that you have that K is discrete? It cannot be CP.
It's important for my personal psychological advantage. I'm more familiar with it. I don't think at this stage you don't need it. The theory works just fine.
Like for
Yes.
CP or
You can take it to be, I think, any complete extension of QP.
yeah, because in some old talks they mentioned something about spherically complete.
Yes, I
fields
asked
and
Peter
stuff.
why they did that, and they said I didn't get a satisfactory answer, so I don't think
Yeah,
it's
so I
necessary.
got an impression from the old time that they had the technical difficulty in functional analysis or something.
Which I'm not going to be doing at all, so it's all algebra.
But no. But the question is whether there is a difficulty or just or not, or maybe it's just trivial to get around it. This is the problem. This is the question.
So I don't know, because so far I've been working with complete discrete valued fields
Okay.
K, just to be safe. Went too far. Oh well. Right. So now, the advantage of completing this group ring in this particular way is that it's big enough to contain the universal enveloping algebra of the Lie algebra of the group. So you can just differentiate local analytic functions in the direction of a vector field, and then evaluate the resulting derivative at 1, and that gives you a linear functional on the ring of k-valued local analytic functions. And that gives you an embedding of the Lie algebra into a distribution algebra, which extends by universal property to a ring homomorphism. And now my starting point of this work is the I'm a terrible historian, so I will try not to miss anyone out. And the following famous theorem due to Bernstein, Volinsky, and Kashiwara tells you how to think about modules over the enveloping algebra. Let me remind you for every dominant regular weight of the maximal torus, and this works over an algebraic closure of the ground field, works over any algebraically closed field of characteristic 0.
When you say dominant, it implies it's integral, or because otherwise you have to Predominant has a positivity. So.
Lambda of H alpha is not in the set -1, 0, 1, 2, 3, 4, 5 for every H alpha.
Not in.
Yeah.
Okay.
Yeah. So over C, of course, it's geometric, but here I'm just making the minimal conditions needed to make the proof go through. Right, so representations of a semisimple Lie algebra with a fixed action of a center, assuming it's nice enough, are equivalent to twisted D modules on the flag variety, which are quasi-coherent as A modules. So you can, this opens the door to applications of methods from algebraic geometry to the study of representation theory of Lie groups and Lie algebras, and in particular led to the first proof of the Catalan-Lustig conjectures. So the goal of this work is to prove an analog for this locally analytic distribution algebra. The hope being that this embedding is nice enough to support such an extension. Well, clearly, in order to do this, I will need to understand the analysis side of things a bit better, right? What is this completion of the group ring, and in particular, what is... This is purely algebraic, this is some kind of analytic guy, so what's the relationship? We need to understand the completion better. So I'll try to give my take on it. So the first question from the point of view of this presentation to ask, I think, is, well, what is the closure of U of G inside dgk? So this is some kind of Frechet algebra. What is the closure of the enveloping algebra? I'll tell you. So I define standard monomials in some basis for the Lie algebra over K, and let me make a definition. So here's the first time where these caps come in. What is this cap? It's a set of I'm sorry, I don't know standard notation for the set of non-commutative monomials, but this means just the commutative power series ring stripped of its commutative multiplication, just thought of a set of formal power series with fixed ordering, right? No x2, x1s, x2s, just honest power series, commutative power series, but on it you can define a multiplication.
So associative but not commutative.
Correct. Yes. And I can't define it all of it, only on those power series which are convergent everywhere on the dual of the Lie algebra. So this definition seems to be dependent on the choice of basis I've chosen. It doesn't. You can check quite easily. It doesn't depend on the choice of basis. It's an intrinsic ring extension of the enveloping algebra. It can be defined this algebraic way with no mention of completions, topologies.
Exponential to make symmetry, to make symmetries. Symmetric algebra over the algebra is not as an algebra but a vector space isomorphic to each. Okay, that's another version. And so it completely makes sense.
Okay. Yes, yes. But I would have to take yes, S of G.
I don't understand exactly what you're doing, because if let us say you're taking a billion Lie algebras, then you must the symmetric algebra is the enveloping algebra, so it is commutative, but you claim to be taking non-commutative power series. So for every monomial, all the permutations are different monomials in your convention.
That's what I said.
So it's too much. You get something bigger, it will not be. I don't see how you map, for example, UGK into this, because you can write everything in UGK. Once you fix an ordering of the basis, you can write everything by Poincaré-Birkhoff-Witt as a sum of monomials which are arranged according to this ordering. So then you can use it to define them. I don't know exactly how you.
It's exactly what I said.
Yes.
You symmetrize things, and it gets it.
What?
You can symmetrize. I can explain it to you.
So I haven't thought about the symmetrization argument for a while. I believe in a paper of Kohlhaaser, where he computes the center of a distribution algebra, he does use the argument you mentioned. I think it does work, although I haven't looked at it for a while. I just want to think of it as this set, and I can give it a ring structure in a unique way such that the obvious map from algebraic thing into this thing is a ring homomorphism.
But what is the obvious map?
Xi goes to Xi. The linear map.
Relations in the enveloping
Xi xj minus xj xi equals bracket xi.
But the relations are not verified in the.
But I've forgotten the ring structure here. This is now purely a set of a vector space. No more. Forget about the actual ring structure here. It's just a set of power series. I don't want to multiply them in the usual way. I'm asserting that there is a ring structure on it.
No, but if you use this seems to be too large. Perhaps you want power series arranged where the x1, xd are arranged in their order. That is only monomials of the form x1, a1 up to xd, ad, and not in the other ordering. Because if you have all those things, then the relations that you mentioned, you see, x1, x2 minus x2, x1, it's.
So maybe could we postpone a little bit?
Maybe we can discuss it.
Yes. I will explain it to you at the end.
I'm sorry for not making this sufficiently clear. So let's just define that to be the Arens-Michael envelope, and then the theorem, essentially due to Schneider and Tasselbaum, says that the closure of is this Arens-Michael envelope, and so the strategy is to first localize UGK cap, localize in an imprecise sense, in the sense of proving an analogous theorem to the Bedamson-Bernstein theorem listed later there, and then extend to the distribution algebra. Okay. So I want to explain how to do this at least. So, and I want to say why rigid analytic quantization So another invariant way of presenting this set of power series, convergent power series, is as the ring of rigid analytic, everywhere globally convergent functions on the dual of the Lie algebra. And this is only as a Frechet space. Yes, rigid analytic. And again, I've forgotten here and here, I've forgotten the ring structure. I just want to say this is true as vector spaces. Now, one of the main parts.
Yeah. Okay. We lost Beijing? No. No, we lost Beijing. So we lost Beijing. So we wait just a few minutes to get Beijing again. François, est-ce qu'on peut avoir Pékin de nouveau? Pékin a coupé.
Faut qu'ils nous rappellent,
C'est à eux de nous rappeler. Bon, okay.
Ça, c'est le Japon.
Ça, c'est le Japon. They will come.
So, if you want a precise definition of the ring structure on this set, I will give it later. I will give a precise formula which gives the ring structure.
No, the question is, I thought it is not the right set, not that the... Because when the algebra is commutative, you should use commutative power series. So...
You see, it's the convergent functions are very...
No, but I didn't understand what is the set, let us say. I didn't understand what is the set, but maybe you can explain it in the end.
Yes.
It's not important.
Okay. Okay, so wait.
Maybe I can clear the board whilst they're waiting.
Yeah. Okay. Yeah. Okay. So Beijing is again here. Okay. Good. So both of you are.
I want to take the middle board, but this is probably stupid. I get the middle board. So, observation, the way localization works involves an algebraic quantization. So this is intuition. Let me try to make it a little bit more precise. I will write down 3 rings and 2 ring maps connecting them, which are non-commutative, which are filtered, whose associated gradients are geometric. So this guy quantizes just affine D space. What is U lambda? So I take the enveloping algebra and I mod out by an ideal, a two-sided ideal generated by a maximal ideal of the center of the enveloping algebra, generated by things in form z minus lambda of z. That thing quantizes the nil cone and whatever d lambda is, it also has an increasing filtration, ring filtration, a filtration of sheaves of rings whose associated gradient is basically the ring of functions on the cotangent bundle of the flag variety. So there is filtration on d lambda. When you take the associated gradient and you take sheaf spec, you get a variety which turns out to be the cotangent bundle of the flag variety. And there is a well-known map connecting the cotangent bundle of a flag variety with a nil cone called the spring resolution. The cotangent bundle of the flag variety is a resolution of singularities of the nil cone.
D lambda corresponds to the infinitesimal central character?
Yeah.
Okay.
Lambda is, yeah.
What is the quantization now?
In this context, I just mean good or this is that, nothing else. I don't want to make anything, this is just philosophy. It would be very nice if I could make it more precise. But it tells me how to proceed in the p-adic situation. To localize this, well, I can do the same thing in the p-adic setting because I still have the Harish-Chandra center sitting inside the enveloping algebra, and I can still mod out by maximal ideals in that. What we need to do, we need to define some kind of fresh phase space completion of d lambda, which will be a rigid analytic quantization of the corresponding object, namely the rigid analytic variety underlying this algebraic variety cotangent bundle of the flag variety. Okay, so this was all motivation. Now I can maybe write down some precise statements, and maybe the motivation will help you to understand why I'm writing them down. So now I will try not to say anything else about twists because they're just confusing and don't present any technical difficulties that I've found yet. So untwisted decap modules is what I want to talk about next. And this section is joint work with Simon Wadsley. Definition. Let X be a smooth athenoid variety over the ground field K. A Lie lattice on X is a finitely generated submodule curly L of the derivations of O of X, finitely generated over the subring of power-bounded elements. such that, well, its lattice it's a Lie algebra, and it acts on power-bounded elements. And so a more correct way to say this is that it's a K circle, comma, OX circle Lie algebra, or a Lie algebroid over the integral structure. Given any such Lie lattice, and there are plenty of such things, because whenever I have a basis for T of x over O of x, say V1 up to Vd, maybe the Lie brackets of these guys don't lie inside the OX circle submodule generated by them. But I can multiply them by a huge power of pi, and then they will be. But to any Lie algebroid, I can associate its universal enveloping algebra, U of L. Okay?
Which is what?
It's the smallest thing generated by... So, what is a Lie algebroid? You need a commutative ring, and you need a Lie algebra. You need the Lie algebra to be a module over the commutative ring. So that means that the commutative ring acts on the Lie algebra, and the Lie algebra then acts on the commutative ring. So in the basic example is T of x and O of x. And so the enveloping algebra of T of x is going to give you D of x. Okay? And this works in great generality. All you need is just a commutative ring and the Lie algebra and the module.
Real universal algebra.
Yes.
Is a proper category.
Yes, yes. Completely general. Okay. Defined first by Hertz in 1953, and then Reinhardt, and then it just seems to have got lost.
You said that? I know about Reinhardt, but you said there was a...
Hertz, pseudo Hertz, maybe? H-E-R-Z? I don't know.
Hertz.
Yeah. Anyway, so you have U of L, but then I can periodically complete it. And then I can invert pi, just like we do in rigid geometry. Okay, so this will be some non-commutative Banach algebra over K. And under these assumptions, actually, will be Noetherian. But it unfortunately depends on this choice of lattice integral structure. So we get rid of that choice by taking the inverse limit over all things. And this is just sort of elegant, but you only need just one Lie lattice, and then big pi power multiples of it will be cofinal with big pi power multiples of any other Lie lattice. And so I could have just done inverse limit of u pi to the n L k hat. And so geometrically this corresponds to stretching along big balls inside the cotangent bundle. Okay?
You are in affinoid variety, so you don't have the problem.
Just affinoid for the moment.
You don't have the problem of gluing.
I'm trying to do that now. Okay, I will state theorems. Just affinoid now, yes. So, example. So here is a Lie lattice. Well, obviously you can take K circle, take x, del x, and then multiply it by big power of pi, and it needs to be non-negative here, otherwise it's not Lie algebra. And then if I do this construction, I will get a Banach algebra, non-commutative, which as a k-vector space and as a Banach k Tate X module is isomorphic to the Tate algebra in two variables, k, x, and a new variable. Okay, that's what it looks like.
Oh, you are fixed N.
Fixed N.
It is a non-commutative. You say that it is. It is isomorphic as a module to the commutative guy. Okay, this is what you said. Okay.
So, and d cap is just the intersection of these non-commutative rings. Okay? So it contains, in particular, the Tate algebra K Tate X. It will contain del, so it will contain the d of x, as it were, so the hybrid thing, affinoid in the base direction and polynomial in the cotangent direction, and more stuff on top. And that's what it is. And this is yep. And I should say, of course, this is just O of T star x as a threshold of x module. And so, because of this, this is morally, at least in my mind, a rigid analytic quantization of T star x. So, theorem. We've thought quite a lot about this now, and we're pretty sure this is the right definition. In particular, it globalizes nicely. So this definition satisfies Tate's theorem. So take the standard site associated to a rigid analytic variety, just open affinoid subsets, or a G topology in the sense of BGR if you prefer, and then D cap is a sheaf. And
The sheets. Now comes the sheets.
yes, we're vanishing. Hi, check, how much? Okay, but it looks a bit wild, doesn't it? If I want to have some kind of decap modules, I need some control. I need some finiteness conditions on modules over decap x and sheaves of decap modules. Fortunately, Schneider and Teitelbaum have already worked this out. They have defined a nice category of modules called code-miscible modules in particular, which will give a definition of what code-miscible meant at the start of the talk, because they did prove that the distribution algebra of any compact periodically group is Frechet-Stein. So that's the definition I'm about to give.
So a question on your statement. So when you say vanishing higher check cohomology, do you refer to check to coverings of X by affinoids or to covering of an affinoid by smaller affinoids, or both cases?
Both cases. Both cases.
Okay.
Because surely a small affinoid is also a affinoid. And the definition is.
I mean, you can
It's
cover
a functor.
you can cover an affinoid by finitely many smaller ones.
Yeah.
Take the check complex, and you can say that
Yes.
that this is a cyclic, and you
Yeah.
can also cover X itself. So you can take the cohomology of X itself, which is not affinoid,
X was finite. X is
So
always.
here it's just you are still not finite.
X is still a finite. I'm not saying
So the
anything.
next step is what you think about.
Okay, I was confused.
Still a finite. I will say when it's not.
You are in advance.
Okay, excuse me for this.
No problem. Thank you. So. Suppose we have a tower of Noetherian K Banach algebras with, I'm going to be sloppy and say flat transition maps. I think the definition only needs one side, maybe on the right, but in all cases I know it will be true on both sides. Suppose you have such a situation. Then you can take the inverse limit, and then the definition is that the inverse limit is an example of a Frechet-Stein algebra. Okay, so what? Well, this gives you, first of all, it's kind of nicely independent in the choice of presentation. It can happen that you have two different towers giving rise to the same inverse limit as K Frechet algebras. But as long as you have one, then the category of finitely generated modules will be the same. Definition. Whenever you have such a Frechet-Stein algebra, you can define a co-admissible module. A module is co-admissible if whenever you say think of it geometrically, it's some sheaf defined on the whole cotangent bundle. Whenever you pull it back to some bounded affinoid subset, it's coherent. So it's, coherent, basically. But
You did not finish it.
I'm very sorry. Is a finitely generated a module for all n.
This is algebraic tensor product or
Completely algebraic.
what?
Only algebraic? No, just algebraic, yes. Algebraic tensor product. And so it's quite amazing that with this definition you get a nice abelian category. Well, the proof is not deep. So let curly C of A be the category of co-admissible A modules.
So to avoid misunderstanding, so a finitely generated module is co-admissible.
Yes, that's accurate. But not convex. The problem is that Frechet-Stein algebras are not Noetherian, unfortunately. So there are lots of examples of finitely generated modules which are not finally presented. So our next result is that our D cap rings are always Frechet-Stein affinoids.
When you say is an abelian category, usually this is in such a context. There is an ambiguity whether you mean the kernels of kernels exist in this category or that they are equal to the ones in the bigger one of all A modules.
I think both are true in this setting. every abstract homomorphism is continuous, kernel is closed. It's very nice. Yeah. But you actually want to be careful. Okay, so with this in hand, I can define the global version of D-cap coherent modules. M is co-admissible if, well, obviously I would want its sections on the near phenoid to be co-admissible in the sense I've just defined, but I do need an extra condition, which is analogous to quasi-coherent in the algebra geometric world. I'm very sorry, can I not go into the details of this symbol? There is a very nice and very obvious thing you can do. You can do a completed tensor product. It's basically tensor product as Frechet spaces, but you can make sense of it in the situation, and I do require that. Whenever I have an inclusion of a phenoid V inside U, then basically M of V is completely determined by M of U in a functorial way.
So here X is not an affinity.
That's correct.
And it means that you
So,
extended
yes,
already the definition
yes,
of
I should
affinity.
say that, yes. I'm very sorry. At this point, I say, right, so now, from now on, X is general.
Okay, so you glue the previous definition.
Yes.
Is it true that M is the inverse limit of M tensor A, N?
Yes, it is.
It follows from the definition, or you have to put it as an extra
I
condition?
don't remember the technical details, but I think you have to do a bit of work for it. It's a theorem. You have to show that R1 limit vanishes at some point. You have to do something. I'm sorry, I'm so used to using it as a black box, I don't remember the proof.
As it is, whenever the algebraic tensor products are finally generated, the module is the inverse limit. Something like this.
Yes, that's right.
Okay.
Yes, that's right. It's a theorem that if you define it the way I did. Yeah.
Take a little bit of time deleting your blackboard. Begin to come back.
So, in fact, you confused me. No, so far I think, let me take it back that I have extended. X is still a phenoid here, okay? I've just defined sheaves, yeah, just still a phenoid here. I do have here, now extend, so follow my program. So, can I remove this now?
Yeah, you can remove and wait a little.
So, with X still a phenoid, CX will be in the category of co-admissible sheaves of D-cap modules. On X. WX is still a phenoid here, okay, but now they're sheaves at least. 3. that is an equivalence of categories. Between modules, so code-miscible modules over d cap of x, and sheaves, which are code-miscible in the sense defined. And so it follows that the sheaf category is also abelian. And I think I do mean it to be as a full subcategory of the category of sheaves and modules. So now we extend. No. Extend by sheafification. D cap and Cx to every smooth rigid analytic space. And I think, well, we've got 3 definitions of Cx, but I think the one I gave actually works in general. You parse it. Where's it gone here? So if you take this definition, X is no longer a phenoid, and you impose these conditions, it's a theorem that this category is the same as that you would have got if you were to, have a sheaf which had the property that there was some covering such that on each covering its restriction was log of something code-miscible. So it kills theorem. Can I lift? Sorry, I'm terrible with boards. Can I erase this? Yeah. So, here's our next theorem. So suppose I have X, which is a closed, smooth subvariety of Y, smooth, rigid. I have d cap modules of X, and I have d cap modules of Y, and I can ask, what's the relationship? And so it turns out that the d cap modules on Y, having 0 sections away from X, are equivalent to the d cap modules on X. So I have stated these as theorems because I've written them up and I'm 99% confident they're true. And anything after this is not written yet. I'm still confident that the next one is true, so maybe. They're not written yet, so maybe I'll put quotes around them to be safe. The next expected theorem, 5. Denison-Bernstein localization. Suppose I have a linear form on H with values in K, H being the Lie algebra of a split maximal torus in G as before, so let's suppose it's split for simplicity. But it's a Lie algebra theorem, so I don't care. And dominant in the way I've defined earlier, and regular meaning that the stabilizer in the veil group under the shifted action is trivial. Then so actually I have not defined d lambda cap, but we have a definition which is valid. So you can define u of curly L cap for any k comma ox Lie algebroid curly L. Not just a tangent model, you can take a twisted thing. So everything now here makes sense. Bn is a smooth rigid analytic variety. You can talk about coadmissible sheaves of d-cap modules, which are defined locally and glued together on aphenoids. And when you take global sections, you will get modules over the Arens-Michael envelope of the Lie algebra.
B is a flat manifold.
Yes. And I should have said, I'm very sorry, one of the easiest examples of a fresh Stein algebra is the Arens-Michael envelope. The Arens-Michael envelope UG cap that I defined as a set of power series, you can define it as U of L cap, where L is a finite dimensional Lie algebra. You take the inverse limit of the U of finite rank things. Okay. So this gives you a bridge between modules over Arens-Michael envelopes. And these sheaves. So
It's completely proved, or it's expected?
It's not written. I believe it to be completely proved, but it's not written.
That's what you put petition.
It's not written, so. I mean, at the very least, I'd be very confident if I was to impose the same condition on the prime P as I had in my other paper on formal things, because there we needed to use techniques of Bezirkavnikov to actually compute global sections, and they, for technical reasons, they're assuming P is a very good prime. And so I think we can just write down a proof using that. But this theorem should not depend on P at all. It's just characteristic zero. Anyway, so corollary. Why do we care? Well, you can, for example, construct modules from geometry. You can construct irreducible modules in the following way. Of course, this is an idea as old as the original localization theorem, but it's nice that it works here. So I have maybe a point in the flank variety. Maybe I have just a fun, trivial vector space, one-dimensional on it. I can D-module push forward it to a skyscraper sheaf on the flank variety, take global sections, and this will give me some kind of completed Wehrmann module for the Lie algebra, for example. But of course I don't have to take a point, take any closed subvariety. maybe with something interesting on it.
So P1 is the flag variety?
It's the rigid analytic variety associated to the flag variety of the algebraic group G.
Okay, so it's proper in the sense of rigid analytic
Correct.
geometry.
Yes.
And Y is a closed rigid analytic.
So it's also proper and not therefore algebraic.
Yeah, so it's a global one. It's not just because depends on which topology. Okay, when you use okay.
I'm using the analytic topology. Closed embedding.
Okay, depends what you mean by close embedding.
But also the because rigid graphic.
Okay, but any affinity. Okay, I understand it.
Then I'm very sorry.
So it is algebraizable by GAG. Okay.
I get a simple code miscible module over the Aaron's recommended. I'm out of time, and I haven't said anything about equivariant things. What do you want me to do?
So, do you want to take maybe 5 minutes? It's okay? Or just to see. I think you cannot go more than 5 minutes.
Not no more than 5 minutes. Okay, sure. And then I will give a definition, and maybe I'll just sketch the extend it again because it's not written.
5 minutes. Okay.
So let's just for safety take G to be compact. As before. X to be a smooth phenoid, and G acts on X continuously and differentiably. So
That
that's
G is open.
G is open, yes, open compact, yeah. So here, obviously, by punctuality, it will preserve the ring of power-bounded elements in O of X and induce an action on the reduction of X. And let's assume that the action of G on the reduction has finite image. And indeed, the action of G on any OX circle, mod pi to n OX circle has finite image. At least that. So this is what happens when G is an open compact subgroup of G of L acting on the flag variety. You might have a small group stabilizing a smaller phenoid in the flag variety. Then you can do the following construction. It's don't have time. You can take d cap of x, or dx of cap, it's the same thing. I can take the abstract Q group ring. That's stupid. It doesn't take into account the topology of G, and then I complete it a bit. How do I do that? I look at various things involved in the definition of d cap. There were these Banach algebras. And then if, for any fixed L, if I let G approach to 1, if I look at very small subgroups of G, they will stabilize it. And in fact, they will be acting as exponential of Lie algebra elements. Since I don't have time, I'll just say that this is the inverse limit of all possible pairs L and N where this makes sense. And alpha is just the derivative of the action of G. So it's a Lie algebra homomorphism from Lie algebra of G into G of X in this case. Because it's a Lie algebra homomorphism by the Baker-Campbell-Hausdorff formula, this expression here is a group homomorphism from N into the group of units.
François, le tableau.
So the semi-direct product is taken purely algebraically?
Yes. Yes.
Then you complete.
And so this makes sense. And if I can define look at just G stable. Open a few lines. In X. So it might be empty if G is big enough, so that's not good. But G is small, it will have at least some elements in it. And then expected theorem 6.
Will you write X subscript something?
X W slash G. Just notation. I want to use that notation to define that set. This thing should be a sheaf on this G topology. We'll have to find out coverings. Again, of Fresh-Stein algebras. And again, with vanishing higher check homology. And finally, let me just remark that here's another definition. Let X mod G sub W be G stable quasi-compact opens subsets of X. Or maybe not affine, but finite unions of things which are G stable. Then this is a good G topology because, well, sheaves on the rigid space are the same things as sheaves on the adic space in the sense of Hubert. And G acts on the adic space, so I can take X adic mod G as topological spaces. I give it the quotient topology, and then I pull back the site structure.
So X is...
X at the moment is just a phenoid classical rigid space.
Just a phenoid, because otherwise you don't have global, okay.
But
Okay.
none of this is written. So. Work in progress. Yeah, all this is work in progress.
Yeah, so maybe we should conclude and then we continue the discussion.
Okay, let me write down a remarkable theorem. So that's a Hubert space. And so the expected theorem is, well, given if you believe theorem 6, then you might believe that I can define some version of coadmissible D cap star G modules in the same way, gluing locally. Because everything is locally, at least Fresh-Stein. And so finally, theorem 7. GB open compact. Then lambda as before. And then I can write down co-admissible Of course, this has not been defined in the stock, but whatever it is, it's going to be equivalent to what I want, namely the objects on the representation theoretic side, which are co-admissible modules over distribution algebra, which are duals of admissible representations which occur in number theory. And of course, because I'm working with lambda, I need to impose a fixed infinitesimal central character. I'm sorry for taking so long. Thank you very much.
Thank you. So, maybe we take first questions from Tokyo.
Question from Tokyo.
Let me see if you're waiting for something.
If there is no questions from Tokyo, so is it okay?
No question.
Okay, then we go to Beijing. Are there any questions in Beijing?
Okay. So I have a question. So in your talk, you define the category CX for the smooth rigid analytic space. Now suppose you have suppose you have a morphism, for example, proper morphism of smooth rigid analytic space x to y. Then how it will take the category CX and CY? Does there exist a well-defined direct image factor from CX to CY?
In the case of a closed embedding, we have a well-defined direct image functor, which featured in the statement theorem for I plus. I believe that it will also work in the proper case, but we have not checked the details. There will be problems in the case when the morphism is not proper.
Okay, so your answer is for closed immersion is okay, and it's your theorem 4, and for other form morphism you haven't checked yet.
That's right.
Am I right?
Yes, but it should be okay. Yes.
It should be okay.
Okay. Thank you.
Thank you.
Other questions from Beijing? No. Okay, so
I think no.
so you can take a few questions from Paris.
No, but there was a question in the beginning.
Yes, so there was some question of foundations in the beginning.
What
Maybe we
is
can,
the definition of those formal series?
yes, we have to discuss them. Maybe we postpone them just after we cut. But are there other questions? Do you have other questions?
No, because this is very far from what I can ask, because I'm not really, I don't know precisely, so I cannot ask questions on
Okay.
this.
So maybe I have just one question. In some sense, here you work always with the rigid analytic variety. So if you take the point of your formal scheme,
Yes, I forgot to apologize that my abstract said via equivariant formal models.
yeah,
And that's because I came up with this definition the last month. Beforehand, I didn't know how to do things equivariantly properly, so I was going to go via Lebok and via formal models, and it just works.
Okay.
You do it. You take the g-equivariant objects and the array node integrate. Yes, so you can form it in that way, but it's just easier to go at it directly. For now, maybe I'll correct it.
Thank you. So I think that's all. Let's thank the speaker again.